The ocean is a vast body of salt water covering about 70.8% of Earth's surface. In English, the term ocean also refers to any of the major divisions of the global ocean, which include the Pacific, Atlantic, Indian, Southern, Antarctic, and Arctic oceans. The ocean holds 97% of Earth's water, playing a critical role in the hydrosphere and being essential for sustaining life. It has significant effects on climate, weather patterns, the carbon cycle, and the water cycle, acting as a massive heat reservoir. Scientists divide the ocean into vertical and horizontal zones based on different physical and biological conditions. The pelagic zone refers to the open water column from the surface to the ocean floor, which is further divided by depth and light availability. The photic zone, extending from the surface to a depth where light is only 1% of surface intensity, around 200 meters in open ocean, supports photosynthesis. In this process, plants and phytoplankton use light, water, carbon dioxide, and nutrients to create organic matter. The photic zone is highly biodiverse and forms the foundation of the ocean's food web. Photosynthesis in this zone is responsible for producing half of the Earth's atmospheric oxygen. Below this zone, light penetration decreases, and deeper parts of the ocean, known as the mesopelagic and aphotic zones, are cold and dark. The continental shelf, where the ocean meets land, is shallower, usually a few hundred meters deep, and often affected by human activity, impacting marine life. Ocean temperatures vary based on solar radiation exposure. In tropical regions, surface temperatures can exceed 30 degrees Celsius, 86 degrees Fahrenheit, while at the poles, temperatures near sea ice are around -2 degrees Celsius, 28 degrees Fahrenheit. Deep ocean temperatures worldwide range from -2 degrees Celsius, 28 degrees Fahrenheit, to 5 degrees Celsius, 41 degrees Fahrenheit. Ocean circulation results in currents driven by temperature and salinity differences, wind, and the Coriolis effect. Tidal currents are generated by tides, while wind and waves create surface currents. Major currents like the Gulf Stream, Kuroshio Current, Agulha Current, and Antarctic Circumpolar Current move large volumes of water, gases, pollutants, and heat, influencing global climate systems. Ocean water contains dissolved gases such as oxygen, carbon dioxide, and nitrogen, which exchange with the atmosphere at the surface. The solubility of these gases depends on the water's temperature and salinity. Rising atmospheric CO2 levels, primarily from fossil fuel combustion, led to greater CO2 absorption by the oceans, causing ocean acidification and a decrease in pH. The ocean provides valuable ecosystem services, seafood, marine resources, and transportation. It is known to host over 230,000 species, with estimates suggesting there may be over 2 million species yet to be discovered. However, the ocean faces numerous environmental threats, including pollution, overfishing, and climate change impacts such as warming, acidification, and sea level rise. The continental shelf and coastal areas are particularly vulnerable to human activities. World Ocean redirects here. For the concept of an ocean world, see elsewhere. Ocean Sea also redirects here. For the 1993 novel by Alessandro Baracco, see Ocean Sea novel. The modern concept of the world ocean was introduced in the early 20th century by Russian oceanographer Yuli Shikalsky, describing the continuous body of oceanic water that envelops most of Earth. This interconnected global expanse is often called the world ocean, global ocean, or great ocean. The idea of an unbroken, interconnected water body with free exchange among its parts is fundamental in oceanography. Etymology: the word ocean originates from Oceanus *, a figure in classical mythology, regarded as the eldest Titan in ancient Greek lore. The Greeks and Romans envisioned Oceanus as a divine representation of a vast river encircling the world. The Greek term *okeanos* has links to Indo-European roots, drawing parallels to the Vedic epithet *asayana*, associated with the dragon *Vyatra, who blocked the flow of rivers. This mythological connection is sometimes depicted on early Greek pottery, showing okeanos with a dragon's tail. Natural history origin of water scientists suggests that significant amounts of water were already present in the material that coalesced to form Earth. During its early, less massive stages, Earth would have experienced atmospheric escape, where water molecules more readily escaped its gravity. Early Earth likely featured vast magma oceans. Through outgassing, volcanic eruptions, and meteorite impacts, an atmosphere composed of carbon dioxide, nitrogen, and water vapor gradually formed. Over millions of years, as Earth's surface cooled, water vapor condensed to create the first oceans. Initially, these oceans were probably much hotter and had a greenish tint due to high iron content. Geological evidence helps pinpoint when liquid water first appeared on Earth. Pillow basalt samples, formed during underwater volcanic eruptions and recovered from the Isua-Greenstone belt, indicate water's presence around 3.8 billion years ago. Rocks from the Nuvvuagittuq-Greenstone belt in Quebec, Canada, dated between 3.8 and 4.28 billion years, also suggest water was present during these ancient times. Any evidence of even earlier oceans may have been lost to geological processes such as crustal recycling. However, research published in August 2020 proposed that Earth may have had enough water from its formation to fill the oceans, maintained in liquid form by greenhouse gases that prevented freezing when the sun was only 70% as bright as it is today. Ocean formation. The origin of Earth's oceans remains uncertain, but it is believed they formed during the Hadean Eon and may have been crucial for the emergence of life. The coastline and structure of the world ocean are continuously reshaped by processes such as plate tectonics, post-glacial rebound, and sea level changes. A global ocean has existed in some form on Earth for billions of years, undergoing various conditions and shapes, sometimes potentially covering the entire planet. During colder periods, ice caps and glaciers expand, reducing the volume of water in the oceans. In warmer periods, the reverse occurs. For example, during the last ice age, glaciers covered nearly a third of Earth's land, causing sea levels to drop by approximately 122 meters, 400 feet. Conversely, about 125,000 years ago, during the last major warm period, sea levels were about 5.5 meters, 18 feet, higher than today. Approximately 3 million years ago, they might have been up to 50 meters, 165 feet, higher. Geography. The ocean covers 70.8% of Earth's surface and contains 97% of its water, leading to the term world ocean, or global ocean. This immense expanse, especially in Earth's early history, might have once enveloped the entire planet, giving rise to the term ocean world. The ocean's distribution is uneven, resulting in a division of Earth's surface into water and land hemispheres and further classification into distinct oceans. Seawater spans around 361 million square kilometers, 139 million square miles, with the most remote oceanic point, known as Point Nemo, located at 48 degrees 52.6 feet S 123 degrees 23.6 feet W in the South Pacific, about 2,688 kilometers, 1,670 miles, from any landmass. Oceanic divisions. The ocean is traditionally divided into 5 main oceans, separated by smaller bodies of water such as seas, gulfs, and bays. Ocean basins. Earth's oceans fill its oceanic basins, which consist of different geological provinces, including continental crusts. In mid-ocean regions, magma emerges from the seabed between tectonic plates, forming mid-ocean ridges. These convection currents push plates apart, while subduction zones, where one plate slides under another, create deep trenches and generate friction, earthquakes, and underwater volcanic mountain chains. These processes result in features such as mountain building and seismic activity near land-sea boundaries. Every ocean basin has a mid-ocean ridge, forming the world's longest mountain range system, which stretches for about 65,000 kilometers, 40,000 miles, and surpasses the Andes in length. However, less than 20% of the ocean floor has been mapped. Interaction with the coastal zone, where land meets sea, includes the shore between the lowest spring tides and the upper reach of waves. A beach is an accumulation of sand or pebbles, while a headland is a point of land extending into the sea, and a cape is a larger version of a headland. Bays, coves, and gulfs are indentations of varying sizes along the coast. Coastlines are shaped by factors such as wave strength, land gradient, rock composition, and changes in land levels. Constructive waves, arriving at a rate of 6 to 8 per minute, build up the beach, while destructive storm waves erode it. High-tide storm waves compress and release air in cliff crevices, causing erosion, while sand and pebbles thrown against the cliff amplify this effect. This process forms a wave-cut platform, which reduces further erosion. Sediments worn from the land eventually reach the sea, where currents transport and deposit them, forming features such as deltas. Human activities, such as dredging, alter these processes and can impact coastlines in unforeseen ways. Measures like breakwaters, seawalls, and levees are constructed to prevent flooding, as exemplified by the Thames Barrier protecting London and the levees around New Orleans, whose failure during Hurricane Katrina led to significant disaster. Physical properties color most of the ocean appears blue, though in some areas it can be blue-green, green, or even yellow to brown. The blue color results from several factors. Firstly, water absorbs red light more efficiently, so blue light is what remains and is reflected back out. Red light can only penetrate to a shallow depth, typically less than 50 meters, 164 feet, while blue light can reach depths of up to 200 meters, 656 feet. Additionally, water molecules and tiny particles in the ocean scatter blue light more effectively than other colors. This scattering occurs even in the clearest ocean water and is similar to how the sky appears blue. The color of the ocean is influenced by substances such as dissolved organic matter, living phytoplankton containing chlorophyll, and non-living particles like marine snow and mineral sediments. Chlorophyll, detectable by satellite, acts as an indicator of ocean productivity, marine primary productivity, in surface waters. In long-term composite satellite images, areas with high productivity appear yellow or green due to the presence of green phytoplankton, while regions with low productivity appear blue. Water cycle, weather, and rainfall. The ocean holds the largest body of water on Earth, comprising 97% of the planet's water. Evaporation from the ocean transfers water into the atmosphere, which later returns as precipitation over both land and sea. The ocean plays a crucial role in the biosphere, covering about 90% of it. Oceanic evaporation drives the water cycle, contributing to around 90% of global rainfall and maintaining an oceanic cloud cover of 72%. Ocean temperatures influence climate and wind patterns that affect life on land, and powerful weather phenomena, such as tropical cyclones, hurricanes and typhoons, often develop over the ocean. As a major part of the Earth's hydrosphere, the ocean is vital for life, contributing to both the carbon and water cycles and serving as a massive heat reservoir that impacts climate and weather. Waves and swell. Ocean surface movements, known as wind waves or undulations, involve the rhythmic rising and falling of the water's surface. Swell refers to the series of mechanical waves traveling across the ocean's surface, commonly noted in sailing and surfing. Wind creates waves by exerting friction on the water surface. A gentle breeze results in ripples, while stronger winds generate larger waves. These waves grow to their peak when their speed matches the wind's pace. The southern hemisphere's roaring 40s, with continuous strong winds, often produces long, rolling swells. Even if the wind subsides, existing waves can continue moving until they reach land. Wave size depends on factors like wind strength, duration, and fetch, the distance over which the wind blows. When waves converge from different directions, they can form irregular, choppy seas. Constructive interference may lead to exceptionally high rogue waves, which, although rare, can surpass 25 meters, 82 feet, in height. Wave components include the crest, top, the trough, lowest point, and the wavelength, distance between crests. As waves near shore and enter shallower waters, they slow down, pull closer together, and increase in height, a process called wave shoaling. When their height surpasses a certain threshold relative to the water depth, waves break, creating a surge of foamy water that rushes up the beach and recedes back under gravity. Geologic disturbances like earthquakes and volcanic eruptions can trigger waves that may result in tsunamis, posing serious threats to coastal areas. Sea level and surface. The ocean's surface serves as an essential reference for oceanography and geography, particularly when measuring mean sea level. Although it generally appears flat, it has slight but detectable topography that varies with the ocean's volume. This surface acts as a vital interface for interactions between the ocean and atmosphere, facilitating the exchange of particles that enrich air, water, and sediments. Such exchanges contribute to the nourishment of life within the ocean, on land, and in the atmosphere. Collectively, these interactions and their components form the ecosystems found at the ocean's surface. Tides are the regular fluctuations in sea level experienced by oceans, mainly influenced by the gravitational pull of the Moon on Earth. Although tidal forces impact all matter on Earth, their effects are most visible in the ocean due to its fluid nature. While the Moon's gravitational forces are the primary driver of tides, they are also influenced by the Sun's gravitational pull, Earth's rotation, and the presence of continents that disrupt the movement of ocean water. Tidal forces vary more significantly with distance than basic gravitational forces. The Moon's tidal influence on Earth is more than double that of the Sun's, despite the Sun exerting a stronger overall gravitational force. Earth's gravitational force on the Moon is about 20 times stronger than the Moon's on Earth. The Moon's gravitational pull creates bulges in Earth's oceans on the side facing the Moon and the opposite side, resulting in high tides. The sides perpendicular to these bulges experience tidal troughs. Due to the Moon's orbit and Earth's rotation, a full tidal cycle takes about 12.5 hours. However, the presence of continents alters the flow of these tidal bulges, so local tide timings often deviate from the Moon's direct position, necessitating the use of tide tables for accurate predictions. During each cycle, ocean waters rise to their highest point, known as high tide, and then recede to the lowest point, or low tide. As water withdraws, it exposes the foreshore or intertidal zone. The height difference between high and low tide is known as tidal range or tidal amplitude. During the full and new moons, the combined gravitational pull of the Sun and Moon leads to higher, spring tides, while during quarter moons, neap tides, with lower tidal ranges occur. In open oceans, tidal ranges are typically under 1 meter, but along coastlines, they can exceed 10 meters. The Bay of Fundy and Ungava Bay in Canada have some of the highest tidal ranges in the world, reaching up to 16 meters. Other notable locations with significant tidal ranges include the Bristol Channel, Cook Inlet in Alaska, and the Rio Gallegos in Argentina. Tides differ from storm surges, which occur when strong winds and low-pressure systems force water against the shore, raising the ocean's surface significantly above normal high tide levels. The average depth of the ocean is about 3,688 meters, 12,100 feet, with nearly half of the world's marine areas being over 3,000 meters, 9,800 feet, deep. The deep ocean, defined as regions below 200 meters, 660 feet, covers approximately 66% of Earth's surface. The deepest part of the ocean is the Mariana Trench in the Pacific Ocean, near the Northern Mariana Islands, with an estimated maximum depth of 10,971 meters, 35,994 feet. The Challenger Deep, the trench's deepest section, was named after a 1951 British survey. In 1960, the manned submersible Trieste successfully descended to the trench's bottom. Oceanic zones. Oceanographers divide the ocean into vertical and horizontal zones based on physical and biological characteristics. The pelagic zone refers to the water column of the open ocean and is further classified by depth and light availability. The ocean's vertical zones, defined by light penetration, include photic zone *, the uppermost layer where light is strong enough for photosynthesis, typically extending to about 200 meters in the open ocean. This zone supports the highest biodiversity, as phytoplankton and plants produce organic matter through photosynthesis. Most of this organic matter is consumed within the photic zone, although some sinks to deeper layers. The pelagic portion of this zone is known as the epipelagic. Mesopelagic zone, twilight zone, below the photic zone, where light is minimal and insufficient for photosynthesis. Aphotic zone, the deep ocean zone where no sunlight penetrates. Organisms here depend on falling organic material, marine snow, or alternative energy sources like hydrothermal vents. The pelagic zone is further classified by depth and temperature. Mesopelagic zone extends to a depth where the temperature reaches 12 degrees Celsius, 54 degrees Fahrenheit, typically between 700 to 1,000 meters. Bathypelagic zone, spanning 700 to 1,000 meters to 2,000 to 4,000 meters, with temperatures between 10 and 4 degrees Celsius, 50 and 39 degrees Fahrenheit. Abyssopelagic zone covers the abyssal plain, reaching depths of about 6,000 meters, 20,000 feet. Hadalpelagic zone, found in oceanic trenches, ranging from 6,000 to 11,000 meters, 20,000 to 36,000 feet. Benthic zones, found along the seafloor, align with these deepest regions. Bathyal zone extends down the continental slope to about 4,000 meters. Abyssal zone corresponds to the abyssal plains between 4,000 and 6,000 meters. Hadal zone matches the hadalpelagic zone in trenches. Distinct boundaries within ocean layers can be defined by water properties. Thermoclines, boundaries where temperature sharply changes with depth. Haloclines, layers with significant salinity shifts. Chemoclines, areas with pronounced vertical changes in chemical composition. Pycnoclines, layers with significant density changes, often coinciding with thermoclines and haloclines. The colder, saltier, and denser deep water beneath the thermocline helps drive global ocean circulation. Deep water temperatures range from -1 degree Celsius to 3 degrees Celsius, resulting in an average global ocean temperature of 3.9 degrees Celsius. Horizontally, the pelagic zone is divided by proximity to land. Neritic zone, waters over the continental shelves, including coastal regions. Oceanic zone, open waters beyond the continental shelves. The littoral zone, or intertidal zone, lies between the high and low tide marks and serves as a transition area between marine and terrestrial environments, influenced by the tide's ebb and flow. Volumes. The total volume of water in Earth's oceans is approximately 1.335 billion cubic kilometers, 1.335 sextillion liters, or 320.3 million cubic miles. Overall, Earth's water supply is estimated at 1.386 billion cubic kilometers, 333 million cubic miles, which includes water in various forms such as gas, liquid, and ice, spread across soil moisture, groundwater, permafrost, oceans, seas, rivers, lakes, wetlands, glaciers, snow and ice cover, water vapor in the atmosphere, and within living organisms. Of this, 97.5% is saltwater, while fresh water makes up the remaining 2.5%. Most fresh water, 68.9%, is locked in glaciers and polar ice, with 30.8% stored in groundwater, and only 0.3% found in accessible freshwater bodies like lakes and rivers. The Earth's hydrosphere has an estimated total mass of about 1.4 times 10 to the 18 tons, which is roughly 0.023% of Earth's total mass. Around 2 times 10 to the 13 tons of this mass exists as water vapor in the atmosphere at any given time. The Earth's oceans cover about 71% of its surface, approximately 361 million square kilometers, 139.5 million square miles, and the average salinity of seawater is about 3.5%, 35 grams of salt per kilogram of water. Ocean temperature varies depending on solar radiation. In tropical regions, surface temperatures can exceed 30 degrees Celsius, 86 degrees Fahrenheit, while polar regions hover around -2 degrees Celsius, 28 degrees Fahrenheit, the temperature at which sea ice forms. Ocean water circulates constantly. Warm surface currents move away from the tropics, cool, become denser, and sink.